Coming up on this episode, Microsoft CEO Satya Nadella has stated that Microsoft's goal is to compress the next 250 years of chemistry and materials science progress into the next 25 years.
If we could simulate these things, we could simulate vast numbers of different candidate molecules, candidate reactions, use that to then narrow down to a small set which would be useful, and then test them in the lab.
Scientists are on a mission to drive new discoveries that will solve the hardest problems humanity faces. It's a beautiful way to describe some of the very difficult problems that your team and, of course, many other researchers related to this are working on. Do you think that humankind has the ingenuity to solve some of our biggest environmental and scientific challenges? Welcome back to another exciting episode of Future Here. I'm your host, Joel, and today we have a genuinely fascinating guest with us. He's a luminary in the world of quantum computing, a brilliant mind shaping the future of technology, and a Microsoft Research Fellow whose insights are at the forefront of innovation. Ladies and gentlemen, it's an absolute privilege to introduce you to Chetan Nayak. Chetan is not just a name in the field of quantum computing. He's a visionary whose work has opened new dimensions in our understanding of quantum mechanics and its practical applications. With a background that includes a Ph.D. and over 30 quantum physics research papers to his name, Chetan has been instrumental in advancing the frontiers of quantum computing. In the interview, we dive deep into the captivating world of quantum computing, exploring its potential to revolutionize industries, tackle some of the most complex problems facing humanity, and even change the way we perceive the universe. We'll also discuss Chetan's journey, his current projects at Microsoft Research, and his thoughts on the future of quantum technology. Future Here. Hi Chetan, welcome to Future Here. Really glad to have the possibility to discuss quantum computing with you. Firstly, can you please introduce yourself?
Yes, I'm Chetan Nayak. I'm a technical fellow at Microsoft, and I head the quantum hardware effort. We're trying to build a quantum computer. I'm a physicist by training, so that's my skill set. But over time, I've branched out, and I understand that to build a quantum computer, we'll need people with different skills, including computer science, electrical engineering, systems engineering, physics, material science, and chemistry. And so I've been broadening my knowledge and skill set to that end. And I'm really excited about the progress and looking forward to sharing it with you.
Great. And before we jump into your current progress, can you tell us a bit about your background and how you became interested in science and tech?
I had the great fortune growing up in New York City to, my parents emigrated there from India before I was born. I was born in New York, grew up there, and I had the great fortune to go to a wonderful magnet school, Stuyvesant High School. There was a test to get in. I and a whole bunch of fellow 8th graders sat for this test, and then those of us that got in were thrown together, basically a bunch of kids interested mostly in science and math and other academic subjects. And, it was just a place where we learned so much from each other and really, engage with science. And from there, I went to college, had some great professors. I should say, it was at that time that I started teaching myself a lot of math and physics, and went to college. And it was there that I, first learned quantum mechanics, and quantum mechanics, solid state physics, the fields that I then went and studied greater detail in graduate school and beyond. I went to grad school at Princeton. My advisor, Frank Wilczek, a remarkable physicist who worked on things in particle physics, where he was one of the discoverers of asymptotic freedom, which underlies the strong nuclear force, but also did, amazing things in astrophysics and condensed matter physics, or solid state physics, as sometimes called. And there, together, we started working on something called the fractional quantum Hall effect, and in particular, within the fractional quantum Hall effect, it turns out there are certain states that have this amazing property, which is that they have quasi-particle or particle-like excitations that are what are quote unquote not abelian anyons. And what that means is, when you take two particles and you exchange them, if they're bosons, the quantum mechanical wave function returns unchanged. If they're fermions, it actually picks up a -1, and that's an effect that you can see in various kinds of interference, and it's the reason for, among other things, is related to the Pauli exclusion principle, and so it's why matter is generally made up of fermions and protons and electrons and so on. But it turns out that in these systems you have these excitations which are collective excitations of the underlying electrons that make up the system, but when you exchange them, actually you can get any phase, and it turns out not just a phase, but the wave function can transform or rotate in some non-trivial way. And we worked this out in some cases, and then I went on, I became a professor at UCLA, and I started working on this and also other things, high temperature superconductivity, magnetism, and so on. And, out of the blue, I got a phone call one day from a mathematician named Mike Friedman, who was working at Microsoft at the time, very distinguished mathematician with, incredible results in topology that I was, vaguely aware of, but not an expert in by any means. And he said, "Hey, I've been reading these papers of yours, and we've been thinking about quantum computing. I think this could be useful." And so I invited me out. He visited me and then invited me to go to Redmond as a visitor. So I visited Microsoft Research for a semester, and we started working on these things, and that kind of laid the scenes for a lot of the work that we did, going forward. He also noticed that I had some, mountaineering pictures in my office at the time, and so he lured me up by saying, "Hey, let's go climb Mount Rainier." So we did both things. We climbed Mount Rainier and also started, really think about the underlying architecture of how we would build a quantum computer in which the underlying qubits are based on these kinds of collective excitations of these very special systems, which are called topological phases of matter, which have this property that they have these excitations that are like particles, and when you exchange them, the quantum mechanical wave function changes. But another way of saying that in a more computer sciencey sort of way is saying, "Hey, I do some operation and it does a quantum gate on some underlying quantum information." And the fact that it doesn't depend on exactly how you exchange them, but just the fact that they're exchanged or not, which is a very discrete topological distinction, gives it this underlying protection that it actually doesn't depend on the details, which is extremely important because quantum mechanical wave functions are kind of delicate. And that's why, in a sense, that's why the world, if you look around, doesn't look quantum mechanical. It looks very classical, but precisely because the quantum mechanical wave function is very delicate. It gets, the wave functions for different parts, like of my room, get entangled, and in the sense the wave function collapses and it looks very classical. You have to work really hard to avoid that ordinarily. And so what topological phases give open up an approach where you could really use the underlying physics of a system to make it more robust. And so that's that. And so I then eventually joined Microsoft full time when we started Station Q, which was the this center in Santa Barbara, on the UC Santa Barbara, initially on the UC Santa Barbara campus, where we started working on these ideas, mostly as a bunch of theorists initially, working with some experimental groups that were receiving funding from us. And then about 6 or 7 years ago, we decided, hey, no, we need to kind of bring this all into one, make a team out of this as opposed to a collection of academic groups, and started building a team, building up labs, and then really in earnest a couple of years ago. So long story short, here we are, and my career changed over that time because I started out as basically an independent scientist, an individual contributor. I had graduate students, I had postdocs. As Station Q built up, I had Station Q colleagues that I worked with, but that was all collaborations of sort of 2 or 3, maybe 5, maybe 10 at most people, basically writing papers. We would work something out, write a paper, we publish. Someone would do an experiment, we would analyze, maybe we would collaborate. And now we're making this transition to, we're trying to build something. We're trying to build a quantum computer. And that's it's a different mindset. It's a big team. And as the team grew, I took on more responsibilities to, from having a few people that I work with to, managing a team of 20 to a team of 100. And so my career has changed and the things that I'm doing have changed. Still actually the same goal. It's just that the problem this problem of trying to build a quantum computer requires a bigger team. And so therefore you work with the team that you need for that particular, the problem at hand. And so for this problem, we need a bigger team, but it needs to really work as a team. And so my responsibilities leading this team are very different than what they were, 10 years ago or 15 years ago.
Understandably. It sounds like you're on a really exciting journey. What do you think personally interests you in the field of quantum computing, or early on, what kind of made you choose that career path?
There is a bit of a gee whiz factor, to quantum mechanics in general. I mean, it's so different from our everyday experience. It's not at all like, our intuition for how the, classical world works. So it almost seems like it can't possibly be true. It just sounds outlandish. And yet, when you work out the equations, it makes sense. It works. Like you couldn't understand atoms. You couldn't understand molecules. You couldn't understand superconductivity or superfluidity or a whole host of things. Which just wouldn't be possible to understand without quantum mechanics. So it's anytime I try to explain it to someone who's not a physicist, they look at me like, this sounds a little crazy. What are you talking about? But it's it's not crazy, or it's just crazy enough. And so it's a remarkable property of nature that it works this way. And as we've discovered and understood these more subtle and complex phases of matter, like topological phase of matter, like I mentioned, we realized just how rich this aspect of nature is. And fundamentally, I think these really beautiful, remarkable aspects of nature, I don't think they're there for accidentally. I think they're there because, we can use them for something. And so, when Peter Shor discovered Shor's algorithm, I think it was on 1994, hey, quantum mechanics, as far as computing is concerned, is not just a problem that we have to worry about, but actually an opportunity that could give that actually we could have more computing power than we could otherwise have and solve problems we could otherwise have. That kind of, set off a realization in my head, hey, there's something here that could really be useful that I'm not, I'm doing physics in some sense. There was an aspect of it that was curiosity-based and exploring and is just, understanding nature is cool and, there's a lot of beauty there. But if it could also be useful for something, boy, that takes you to the next level.
It's a good combo, right? Now, this far in your career, you're highly distinguished in quantum computing research and have been working in the field for a long time, as you mentioned. So how would you say the field has changed since, say, the 90s?
Oh, I mean, we really have learned, as a field, as a community, we've learned an incredible amount since the 90s. I mean, the 90s were really, when we think about it, it was early days. Shor's algorithm was around, and in the 90s, error correction, the quantum error correction with fault tolerance, were already understood that those were possibilities. And people were starting to make qubits of various kinds. It was a little bit of Wild West. There were lots of ideas about what qubit, how you could make qubits. And some of those have already really developed and flowered to an extent. And, we've seen quantum computing systems in academic labs and various companies with, 5, 10, 50, 100 qubits, which is really impressive. This is great work. And, in the 90s, I think we didn't even know enough to know how many qubits are we going to have in 2023 or how good will the fidelities, because they're very delicate, and so the fidelities of these qubits or equivalent of the error rates, you need to be really low in order to be able to do any kind of error correction to make them better. And I don't think back then we had any idea whether that was going to be hard or easy or how far away we were. And so, in the early days, you don't know which way is up. You're trying to orient yourself. You're exploring, all kinds of random things, which is the right thing to do. And now there's a lot more focus. I think we actually, I would say we are at the point that we understand what the problems are now so much better. We have solved many problems along the way, and we have ideas about solutions. But I think that there's now a sense of like, okay, we understand the deal.
That's a really good point. And as an analogy, if you had to compare the development of quantum computers to the history of classical binary computers, how would you describe the current state of quantum computers?
I would say it's actually hard to compare the state of quantum computers to classical computers for the following reason. With the earliest classical computers, there really wasn't, in a sense, there wasn't that much competition, because there wasn't another machine or another technology that you were comparing it to. They just had to be better than a human being could do, or a collection of human beings. Maybe they had to be better than Abacus, slide rule. So we're in really a different situation here with a quantum computer. So I would say, in a sense, it's more like, the history of the automobile, maybe, where, the very first cars weren't that reliable, and if you think about it, a horse was probably better in that time period, because you just had to feed it hay. You weren't worried about where you're going to get gasoline. They're pretty reliable. They didn't break down all the time. You need a license to ride one. So, but cars obviously eventually caught up over time, over decades, and then became very reliable and mass producible, and they changed the game. So we're at the stage where quantum computers aren't better than classical computers, really. I mean, actually, on some very specific things, or on a very specific thing, they've shown that they maybe are slightly better than a classical computer. But for all really useful problems, classical computers are better. And so there's a competing technology, and it's not a sitting target; that's a moving target, because classical computers, the biggest supercomputers are getting better and better. So, you're trying to outrun a moving target, but we do know that if we can build a large enough and stable enough quantum computer, that it will be better than any possible classical computer. But we're not there yet. The progress has been remarkable, but we still have a significant way to go. So we're sort of in that sense, we're in the early days of automobiles, where people have automobiles and you can drive them, but gasoline is hard to find. They break down a lot, and horses are extremely reliable. So we're still sort of at that point. But the progress, I will say, the progress, it's never a straight line of progress. It's always plateaus and peaks. But if you look over time, pretty impressive.
Understandably, the goals and objectives definitely are, if not outlandish, then at least very big. And it's super interesting to get into that part of the discussion. Microsoft CEO Satya Nadella has stated that Microsoft's goal is to compress the next 250 years of chemistry and materials science progress into the next 25 years. So could you please discuss what this means for science?
Great question. And that's really an inspirational quote, actually. So thanks for mentioning it. Yeah, so we don't know all of the things that a quantum computer is going to be useful for. We do know, as I said, about Shor's algorithm, which the government cares about because you could potentially use it to crack RSA, and that's already been probably the subject of various things in fiction, for instance. But the other thing that we are fairly certain the quantum computer will be useful for is simulating quantum mechanics, right? That was Feynman's original. When he first thought of quantum computing, that was the application that Feynman had in mind. And because of the richness of quantum mechanics, because of superposition and entanglement, the description of a system in quantum mechanics is in terms of what's called the Hilbert space. And Hilbert space is extremely vast and therefore very difficult to simulate. So you can simulate, maybe around 50 qubits, on a classical computer. And to add one more qubit, you would need to double the size of a classical computer. And to add 2 more qubits, you'd need to double, multiply by 4. So the size of the space in which you have to do your simulation just gets very large very fast. So there are problems in chemistry simulating chemical reactions, material science simulating materials, which are just beyond the reach of classical computers. And so if you think about problems such as designing new fertilizers, so fertilizers, based on nitrogen fixation, that is based on using the Haber process. That's, it's 100-plus-year-old process discovered by trial and error, and there have been minor improvements on it discovered by trial and error, and it's a very, lengthy, expensive process through trial and error in the lab to try to find, new catalysts like that. And if we could simulate these things, we could simulate vast numbers of different candidate molecules, candidate reactions, use that to then narrow down to a small set, which would be useful, and then test them in the lab. That's the kind of thing that, and a lot of energy is actually used to produce fertilizer, as it should be, because this is what you need to feed people. But if you found a better fertilizer, a better catalyst, so that you needed less energy to do this, and we know that actually, for instance, like bacteria don't use a lot of energy when they capture nitrogen. So there very well could be catalysts that enable this. If we find something like that, we really would enable potentially the production of fertilizer at less energy. Another one that is very much top of mind for a lot of people is carbon capture, because we believe that if we could capture some of the carbon that's being pumped into the atmosphere, we could slow down or even reverse potentially global warming. Again, these are things that are extremely costly, very hard to find through trial and error, and time consuming. And if we could simulate and use that to guide our search, we could really accelerate progress. So, and those are just 2 examples. I mean, there are a lot of these examples within chemistry and material science that if we could simulate these systems better, and some of them are fundamentally quantum mechanical, or the quantum mechanics is an important part of their underlying operation and structure. We could simulate those things, then we would really be able to accelerate progress. So that's what he had in mind, and I think that is really exciting potential use.
Do you then think that due to quantum computing breakthroughs, the world and society will look vastly different in the next 25 years?
That's the hope. That's the goal, is that we want to create a new technology that will give us capabilities we don't currently have. And as I mentioned, there are some big problems out there that we need to solve. So the hope is certainly that a quantum computer, that's the goal. The goal is to develop a quantum computer that can have that kind of impact. It's not just an academic exercise.
And your team at Microsoft has published a public quantum supercomputer roadmap. Yeah. The website states eloquently that our growing global footprint of 8 billion people requires new innovations to reverse climate change and address food insecurity. Scientists are on a mission to drive new discoveries that will solve the hardest problems humanity faces. It's a beautiful way to describe some of the very difficult problems that your team and, of course, many other researchers related to this are working on. Can you please explain what people should expect from quantum computing and its effects in the decades to come?
Sure. So, first of all, I have to say, of course, we are in early days. And as I mentioned, quantum computers are still in the stage like when automobiles were when they were really better than riding a horse. We are in early days, and we have very difficult problems ahead of us in order to build a quantum computer at scale. One of the reasons we published the roadmap was to communicate what our goal is, which really is a quantum computer that can solve initially, our initial target is to be able to solve problems in chemistry that we can't currently simulate and which are very difficult to solve entirely through experimentation, or both costly and very time consuming. And we feel that we don't necessarily, the last 100 or 200 years of development of the Industrial Revolution, based on fossil fuels, we don't have another 100 years to recapitulate that entire history, but for the next 100 or 200 years, using different materials and different chemical reactions and different energy sources and so on. So we have to compress that time, and so increased computational power is one way that we're going to be able to compress that time and accelerate that progress, so that we, the next 100 years can be as good or better than the last 100 and more sustainable. And so one of the directions, and I think maybe in my mind the most exciting such direction, is around quantum computing. It will give us capabilities qualitatively and vastly different than anything we otherwise could have. And the goal, as we said, is to build a quantum supercomputer that can tackle those kinds of problems. And when you think about that, that means that everything has to be envisioned around that scale, which means millions of qubits at a minimum, millions of physical qubits. Physical qubits are then rearranged into logical qubits, which are fault tolerant and error corrected and are the basis of the computation. But in order for us to get to that scale under reasonable assumptions about what kind of, how you would group physical qubits into logical qubits, that means you need to have millions of qubits. And so in order to do that, working backwards, well, here are the various steps that you need. And so that's what that roadmap is explaining. Hey, that's our goal. And that's where, Microsoft is a company. And that's where we see value in doing this.
Great discussion. Also, that is a nice segue into kind of your academic research regarding quantum computers. And your biography page on Microsoft's website states that in 1996, Chetan and Frank Wilczek discovered the type of non-abelian statistics associated with Majorana zero modes, which will be the building block of Microsoft's quantum computer. Can you please tell us what these zero modes are in practice?
Yeah. So maybe one way that's quite close, that's actually not so close to how we were thinking about it back then, but very close to how we're using it in our qubits right now, is superconductors. Very famously, in superconductors, the electrons form pairs called Cooper pairs, and it's because of that pairing that superconductors can carry current with zero voltage drop. It's why superconductors expel a magnetic field, and as a result, typically, ordinarily, superconductors actually, even if they have billions of electrons, they actually care quite a lot about whether it's an even or odd number. So a billion and a billion plus one are very different, because with a billion plus one of them is going to be unpaired. Okay, and there's an energy cost for that because they really want to all be paired. So for an ordinary superconductor, there's a big difference between an even and odd number. It turns out that there are not ordinary superconductors that are what we'd call topological superconductors that have this remarkable property that actually they can accommodate that odd electron without any energy penalty, or very nearly zero energy penalty. And as the superconductor gets larger, that energy penalty goes away exponentially fast. How do they do it? Well, if you have a superconducting wire, it turns out that there are defects at the end of the wire, such that that extra electron with zero energy can sit there, but it's not at the left or the right end. It's actually shared in a weird non-local way between the two ends. And only by measuring both that in combination could you tell whether there's an even or odd number of electrons in the system. And so that interesting kind of non-local distribution of information also means that when you start exchanging these things or braiding them around each other, that the underlying quantum information, which ultimately is encoded in sort of the even or oddness of any pair of these, starts getting manipulated. And we realized back then it's something in these states in what's called the fractal quantum Hall effect, so a very different kind of physics of semiconductors and high magnetic fields, that something similar arises, and we realize that this is not abelian. And what not abelian means is the order in which you do two of these operations matters. So if you do one exchange, I exchange 1 and 2, and then exchange 2 and 3, if I did the order differently, it would make a difference. And so we realized that happened, and we were able to work it out, and we saw, we didn't even have the words at the time, but we see now that, this is actually doing a set of quantum gates on these underlying qubits that you have associated with these things. And basically, those ideas have been developed and have been adapted to different physical situations, and that's ultimately what the qubits we're making right now, that's how they operate. So it's very cool. That's something that I remember back then I was a grad student, and just working something out on a piece of paper, one weekend basically, and the equations just kind of worked out, and it was a remarkable feeling. And now to see in devices that we're building and in experiments to see the same thing actually come to life is pretty amazing.
Really awesome. It brings me chills to hear that. Researching Majorana particles also took me on an interesting reading journey about Ettore Majorana, after whom the particle was named. Majorana worked in Enrico Fermi's research group. Is this in any way related now to what your team's work continues? Of course, related to the Majorana particles, but to what extent are you building on the shoulders of giants in terms of scientists who studied this theoretically, say, almost 100 years ago?
Yeah. So, Majorana is an incredibly interesting character in the history of science, and he wrote very few papers, actually, just a handful, but they're all quite brilliant. So this is the most famous one. But these others are actually very interesting and worth a read for young aspiring theoretical physicists. What he did was, to be completely frank, is very indirectly related to what we're doing, because there was nothing about quantum computing back then. They weren't thinking about superconductors or quasi-particles in superconductors. But he was thinking about, hey, what happens if a particle is its own, if a fermion is its own antiparticle? Okay, and that's an interesting problem. And he solved it in the context of relativity, putting relativity and quantum mechanics together. In that context, how can a particle be its own antiparticle? And early days of thinking about those things. So that's again, it's characteristic of Majorana that he, asked interesting questions and got interesting answers. The name has gotten attached to a lot of stuff that he didn't have much to do with, is the honest truth. And so Majorana's zero modes, it really is, it's a small piece of that, the fact that we have some quantum mechanical operators that are their own, creation operator and annihilation operator, that they're equal to each other. So there's some underlying mathematical similarities, but that's kind of the great thing about, some of these ideas in physics. You develop a little germ of an idea here, and then people build on it, and it flowers in a completely unexpected direction. And I would say that's what's happened here. Probably nothing Majorana would have ever, dreamed of, but some of those ideas, some of the, underlying mathematical relations can be modified and turned upside down and goosed and run backwards and forwards and then used in some other context, and then somebody picks up on it. And so in a very indirect way, some of those ideas have come through.
That's really interesting to hear. And actually on previous episodes of Future Here, we've discussed kind of the need and value of basic science, right? Yeah. So I think people should appreciate the fact that many things might at the outset seem like they don't have much practical applications, but you never know how basic science is then interconnected into other things that take it into a wildly different direction, right?
It's so true. There's a famous book by mathematician G.H. Hardy called The Mathematician's Apology. And, he basically was saying hey, what we do is completely useless. And let me just give you a couple examples. And, and the examples you were mentioning were things like, were all things that ended up being useful later, for one reason or another. So it's really remarkable.
Super interesting. So people who are interested in this area of science should definitely read that book, and I'll add it to the show notes so people can check it out. Well, back to modern day. In July, Microsoft published that your team had achieved the first milestone towards a quantum supercomputer. Oh. Can you please discuss what this was related to?
Absolutely. So, as I mentioned, we got this roadmap, and the roadmap is how do we get to millions of qubits so that we can solve difficult problems in chemistry, right? And so then working backwards, what are the milestones we need to get there? At the very beginning of the first couple milestones are around, we need a new kind of qubit. We've got, as a community, as an industry, there are various different types of qubits, superconducting qubits, ion qubit, trapped ion qubits, etc. And getting to that million scale looks very difficult with many of these systems. They might be interesting up to the 50 or 100. Some of them maybe you could see a line of sight to 1,000, but it looks very difficult to get to that scale. And the criteria there are you need your qubits to be actually pretty small, okay, but not too small, I should say, and I'll come back to that. But they need to be small because quantum computers need to be typically very cold. You need to have them very cold because the thermal fluctuations typically ruin your calculation. And so, as I say, quantum states are delicate. So they need to be kept cold. And and by cold, I mean much colder than interstellar space, like millikelvin or 100 millikelvin temperature. So really close to absolute zero. And it's very hard to keep something, refrigeration technology is such that to make something very cold, it's very difficult to do that at large scale, okay? So if you have something that's big, if you're going to build a quantum computer the size of a warehouse, let's say, well, the refrigeration technology using helium-3, there isn't enough helium-3 on this planet to cool down something warehouse-sized to those low temperatures. So people say, well, okay, maybe we'll make a modular system where we have a bunch of computers, you have to distribute entanglement across them, but that's also extremely hard. Crosstalk and anything involving interconnects is very, very difficult. So, and no really known way how to do that with high fidelity. So quantum computers, the qubits need to be fairly small enough to scale so that potentially you could put 1 million qubits on a single chip. They also need to be fast because you want the answer to a problem in a month, maybe. You don't want something to take years, centuries, or something like that. So the actual length of time for the calculation matters. We know quantum computers can do something that classical computers could never do, not in the age of the universe. But for us, practically, the difference between solving a problem in a month and solving the problem in a year or a century really matters. So they need to be fast. And then the other thing is they need to be controllable, because one of the things that's unique to a quantum computer and uniquely difficult is with a classical computer, with a classical chip like a CPU or GPU, you have billions of transistors on the chip and thousands of control lines. So you can make everything on chip very small, but all the wiring and interconnects to the rest of your system, it's hard to do that with billions of those, right? So luckily you can control it with thousands, and there's something called fan out that the information instructions can essentially fan out from a relatively limited number of control lines. You don't have that luxury with a quantum computer. Every single qubit needs some level of classical control, basically. And so if you have 1 million qubits, it's actually 1 million control lines. And so how do you solve that problem? Again, if something is sitting in the bottom of a fridge at 100 millikelvin, you're going to control it from room temperature. That's very difficult. So controllability. So there needs to be some approach to that, solving that input-output bottleneck. So the controllability, speed, and footprint or size are, those are big challenges. So we knew we needed some kind of new qubit that had the potential of scaling out. Hence the idea was around topological qubits, where you could potentially have the scale be small, operate them relatively fast. They'd be potentially very stable, so you won't have to make those same trade-offs. and controllable because of the digital nature of the kinds of operations you'd be doing with them. So to do that, to make a new type of qubit, which is topological qubit, you need to have control over the material so that you can have a topological phase of matter. That's what it's built on. So we needed to show that we could reliably, reproducibly tune a device into that phase so that we could use it as a qubit. So our qubits aren't the qubits that, in a sense, it's not something that nature just hands us. It's something that you have to make the device and tune it the right way to get into the topological phase with magnetic fields and voltages at low temperature. And that first, what we showed was we could do that. So that was the paper we published. Is we have a number of devices, we have a protocol for tuning into the right phase, we have and verifying that we're there. We developed a lot of device design and fabrication technology in order to be able to do that. And the paper the paper shows the results, and so that's milestone one. We're hard at work right now, and at some point in the not too distant future, we'll be sharing results there that on okay, great, now we make qubits with it and show what those are like. And then the next step is to improve on those qubits, to show that there's an improvement path to make those qubits continuously better and better by there's a key parameter called the topological gap, which basically it parameterizes how stable the qubit is in one of these topological qubits. So we were actually able to measure that, its size in that with that first milestone, show that we can make improvements there and get better qubit performance, and then go to multi-qubit systems, logical qubit, and then ultimately the quantum supercomputer. So it's really exciting. It's the first step on this roadmap, and like I said, we're definitely excited to, in the not too distant future, share further results.
Sounds really exciting. And just for context, I read on your LinkedIn page that your job title was the general manager of quantum hardware, specifically at Microsoft. So it's my understanding that besides just kind of working on the research on a theoretical level, is it true that you also had a significant contribution into what hardware the quantum computers are actually running on to be stable as long as possible?
Yeah, so in the early parts of my career, it was at Microsoft, it was around working at the underlying theory, and design. And the theory, as we understood, the theory kind of morphed into device design. And then that my role grew from the underlying theory to device design and maybe system architecture to an extent to, okay, I also am going to manage the teams that are fabricating and measuring some of these things. And so, my role grew as the Microsoft program, as we turned collections of individuals into a team, my role grew to enable the formation of that team to operate as a team to solve problems that they couldn't individually solve. In other words, we knew that I felt very strongly we need to be more than the sum of our parts of a bunch of different mini projects that are all sort of subscale and not quite connected to each other. We need to actually all be working on one thing to one goal, yes, with various sub-projects within it, but all contributing to that. And so understanding what all these projects are, how they contribute to one whole, deciding sort of how to stitch these together so that we can deliver on each of these milestones, that became much more the focus.
Understandably. And is then your team's approach different from other companies working in the field of quantum computing in general?
Very, very, very different, because the biggest distinguisher, or the most obvious distinguisher between the different companies working in quantum computing, is what kind of qubits are they using, right? Because the technology is still very diverse. It hasn't kind of settled down into one type of qubit or another. People are using all different kinds of qubits. So like I said, there's superconducting qubits, sometimes called transmons, particular type of superconducting qubit. There's ion trap based qubits. There's spin qubits. there's neutral atom qubits, there's qubits, photon-based qubits, and then we're doing topological qubits. So there's 5, 6 different types of qubits, and they all have their advantages and disadvantages. Different companies decide to focus on what to place their bets on one or another for various reasons. Ours has been topological qubits. That's, going back to what I said in answer to a previous question, the motivation there was, hey, we want something that has the potential to, we're not looking for something that is going to be exciting up to 1,000 qubits or up to 100 qubits. We're looking for something that could potentially get us out to where we could solve these big, important problems at millions of qubits. And honestly, in some ways, that's a hard road because there's a lot of delayed gratification involved, because we're not using qubits based on very well understood things where the technology is pretty mature. We're trying to invent a new kind of qubit where the underlying technology is non-existent. So, we have to invent a lot of that in order to get that first milestone, to be able to create the topological phase, which people really didn't understand how to make these things, other than by accident, honestly. We didn't really understand how to make these things, how to verify that you have them, and how to measure them and probe them. So we had to develop a lot of that. But the payoff is, we can we can build a new kind of qubit now, or that's the next milestone, and that we have ideas about we have a way, I should say, a roadmap of making improvements. So, fundamentally, the distinguisher is, we are using different type of qubits. That carries with it lots of other things architecturally, because, as I mentioned, there's this issue of the input output, and so that means it's a different kind of control, and so there are a lot of ripple effects with it. But I would say at a high level, you could say it's the focus on that very large scale that is a distinguishing feature for us.
So it definitely sounds like your team at Microsoft is prioritizing future-proofing, scalability, to be able to build some of the biggest quantum computers first.
Exactly.
What are then some of the biggest challenges quantum computing research faces, in your opinion?
I mean, look, qubits are delicate. So the big challenges are we really need fidelity as a measure of, hey, if you make a qubit do X, try to implement some data on a qubit. Did you actually do what you wanted to do, or were you slightly off? So what's the fidelity? So 99%, that's sort of like how well you're able to do what you want to do. And you can correct errors, but correcting errors is very difficult and subtle, because there are more kinds of errors that you could have with a qubit than with an ordinary classical bit. And so error correcting codes are a little tricky. And also, you don't want to measure the underlying quantum information, because of course then you collapse the wave function and it becomes classical. So you want to measure the errors but not the information. And so those two things together make quantum error correction and fault tolerance challenging. And so we really need qubits with underlying fidelities of 99, better than 99%, 99.9. Honestly, once you scale out and you have other challenges, probably you want to have 99.99% fidelities. And that is really challenging, okay? With small systems with few qubits, you can get that, but as you get to large systems, they aren't going to all have the same fidelity. Some of them will be a little bit worse. There'll be more crosstalk. So having those very high fidelities in the system scales out is a big challenge. So big challenge is fidelities. Then, as I said, this input-output problem. You may have seen some of these pictures of these dilution refrigerators control qubits with this bird's nest of wires coming in, because if you have 100 qubits, it's going to be a few hundred control lines already. So or control and readout lines. So that is a problem that clearly is a massive challenge. Now we have a solution, a potential solution at Microsoft. Our solution is based around cryogenic CMOS, and the idea there is actually we'll put a lot of the classical computing power down in the cold, very close to the qubits, to the quantum plane, and then we'll need a limited amount of communication to the outside world digital communication to the cryogenic controller, which then generates all of the high bandwidth communication with the quantum chip. So we solve, in a sense, or alleviate the input-output problem by making it all happen rather locally in the cold. Which, again, that's not necessary at like 10 or even 50 or 100 qubits. But if you're starting to think about thousands to millions of qubits, then you do need some solution like that, because there's just massive input-out bottleneck. So fidelity of qubits and the I/O bottleneck are kind of like big high-level challenges, and they are reflected in the criteria I said that of course you need something that is like small, fast, and controllable.
Understandably, are you optimistic about how your team and the scientific community will be able to solve some or maybe the majority of these issues?
Yeah, I honestly, I believe in our approach. We've made progress. We're learning new things every day. I don't see any, holes, flaws in the strategy. But of course, the devil's in the details, and we have a great roadmap, but we've got to be able to execute on it. And that's a challenge.
Definitely. In 2020, your team published a research paper called Classical Discrete Time Crystals. Can you explain what these intriguingly named crystals are?
Yeah, so this is a separate line of research. It kind of goes back to my to my previous life as a physics researcher. And so time crystals, this actually goes back to an idea of my former PhD advisor, Frank Wilczek. He said, look, a regular crystal, what it does is it breaks symmetry in space. So ordinarily, the laws of physics are the same everywhere, but in a crystal there are these very special points, which are the points of the crystal lattice, and so it breaks the underlying equations, which are a continuous translational symmetry down to a discrete one, just to the lattice sides. He said, well, could something like that happen in time, where the laws of physics are the same at all times, but then the system, arranges itself into a situation in which it's got like an underlying periodicity? And, the idea it's intriguing, but, there was a lot of questions basically around like, well, is that a ground state at that point? Is it a thermodynamically, is it a thermal state? Like what kind of state, that it basically doesn't quite make sense for a ground state. And so there, or a thermal state without some modification. And so I would say, the idea kind of languished a little bit. It was an interesting idea, but wasn't quite clear how to, what it had to do with nature. And then what we realized, about 7 years ago, and this is a former student of mine brilliant student named Dominic Else, who's now the premier student and my Microsoft colleague, Bela Bauer, was that, if you have a system that's being periodically driven, so it's being periodically pulsed, but closed quantum system, so quantum mechanical, periodically pulsed, or periodically modulated, that actually it could select a different periodicity. So it could select a lower periodicity, so maybe the period is doubled or tripled or whatever relative to the modulation, to the underlying rules of the system. And so in that sense, it's a discrete time crystal because the time translational symmetry is discrete, but it's broken to a smaller, to a lower frequency or higher period. And so it realizes that concept. And the thing is, what we showed is that such a thing is actually stable, that this is an actual phase of matter. It's not some fine-tuned thing, which there were versions even of the original time crystal idea that involved some fine-tuning, but actually this is a robust phase of matter. And then, a bunch of experiments were done that showed some signatures of this. They were, they didn't show every single aspect of the time, quantum discrete time crystal behavior, because the systems are small and there's sources of dissipation, so there's not quite a closed quantum system. But they started to show some of the incipient signature, nascent signatures of a quantum time crystal. So in this more recent paper, we made connections between that and many of the things that were known from classical dynamical systems with period doubling and that kind of thing, to show how basically connecting, showing what the classical analogs are to that quantum phenomenon, and connecting it to things that were known in dynamical systems previously.
And just to clarify, time crystals aren't just a theoretical concept either, right? The discrete time crystals have been observed in labs since 2016 or so.
I would say signatures of. I mean, so there are these experiments that incorporate many of the ingredients, but if you want to be very strict, the very strict definition of a time crystal does involve or at least of a quantum time crystal closed system and certain conditions that are not quite met. So it's a little bit of a extreme situation, and what's realized in the lab is not quite that. But it shows a lot of what showed in a variety of experiments, many of the signatures of time crystals have been observed.
Really interesting. And continuing on more sort of exotic or esoteric kind of issues in physics, then what do you think about the theory of everything? And do you think that quantum computing will play a role in humankind kind of discovering a unified theory of all fundamental forces in the universe?
Great question. That's one of the things that Einstein thought a lot about, of course, in the latter years of his life. At that time, they didn't know about the weak or strong nuclear forces, so he was just thinking about gravity and electromagnetism. Of course, we know a lot more now, and there are intriguing hints that the history of physics has been, electricity and magnetism were two very separate things, and then Maxwell, put together and realized that they're two sides of the same coin, and electricity and magnetism are really the same thing. Actually, since you asked me about my childhood and when I first got interested in physics, I remember, one of my distinct memories from actually high school was having to solve one of these problems where, there's a river flowing and you have to row a boat to the other side of the river, and the river's flowing at, some speed, and you can row at some speed. What's the fastest way to get to the other side of the river? And I remember, I didn't know much physics at the time, but I remember thinking, oh, wait, actually, I don't know anything about relativity, but I know that it's something to do with frames of reference. And I think I can think about this problem as the river's not flowing at all and the banks and the land is moving. And then if you think of it that way, actually it's really obvious how to get across the river. The river's not moving and you just go straight across and you know how long it'll take. And forget it, you don't care where you're laying on the other side, the banks are moving. And so, and in some sense, when you're in a boat in the river and it's flowing, you can actually think of it that way. The water's stationary and the riverbanks are moving. So I remember that kind of distinctly because I solved the problem very fast. It felt almost like cheating that I got the answer that fast, because they wanted you to do some very complicated thing where you were adding vectors for the speed of the river and the speed at which you could row and so on. And then I also realized that, well, let's imagine it's a river of charge. It's charged particles. And then I played the same trick. Well, that river of charged particles, that's a current, and currents generate magnetic fields. And when you're stationary, okay, there's a river of charge and there's an electric field, but the forces that it would apply to something need to be the same, right? The thing, some other charge object is to feel the same force. And so if you do that translation between those two cases, actually you end up realizing that you need length contraction, you need aspects of relativity. And so, that was one of the things I realized, like, oh, okay, this, all these things kind of fit together, electricity, magnetism, they're really the same coin, and relativity. And so it's extremely appealing when you realize that there's almost like a shortcut to an answer when there's an underlying unity to these things. It's remarkable, right? And so I think if it turns out that there's an underlying theory that in reality, gravity, electricity, magnetism, strong and weak nuclear force are all, manifestations of the same thing, then that'd be remarkable. But in the end of the day, it's an empirical question. We'll discover evidence for it, or we won't. Quantum computers will give us some simulation capabilities that we otherwise won't have, and it's certainly possible that that could help give us some clues about how that unification could occur.
Really interesting answer. Thanks for that. Also, discussing kind of recent scientific articles, a Korean article on a substance called LK99, a new superconductor that works in ambient temperature and pressure, has been causing a lot of discussion, especially on the internet. A few weeks later, though, it seemed like the research didn't really hold up to peer review, so it's too early to say. You may be hesitant to comment, but it would be interesting to hear how you would see a superconductor that works in ambient pressure and room temperature. How would it affect quantum supercomputing?
Great question. So you're absolutely right. There's a lot of excitement around this, because if we had something that was a superconductor of room temperature and ambient pressure, it could have the potential to revolutionize a lot of things. I would say most of the people that I've talked to who've been looking at this closely think it's not a supercomputer. There might be something interesting happening in the material, but it doesn't quite look like the resistance is going right to zero. And some of the thermodynamic signatures you expect of the transition don't appear to be there. So there's something intriguing going on there, perhaps. I'd say most people think it's not actually a superconductor, but look, there's going to be a lot of follow-up work, and we'll see. There's always room for surprises. So, and even if it turns out that it's not, hey, maybe this gives us some hints about what you need in a superconductor, and people, take this as a starting point and change it and something else works. So let's see. Jury's still out. It's this particular LK99 is probably not a room temperature ambient pressure superconductor. But if we did, it turns out that being a superconductor alone is not quite enough to make quantum devices, because quantum devices are still pretty small, and the properties of superconductor, like I said, this even oddness, the parity, whether it's an even odd number of electrons, and whether or not the superconductors, when you make them small, whether there are unpaired electron states in them that sometimes are said to poison the quantum device. There's a lot of issues, very practical issues around fabrication and properties of, mesoscopic or nanoscale devices that would still have to be worked out. So it would be no guarantee that this would be a superconductor that would be kind of amenable to being turned into nanoscale device. But if it were, wow, it would absolutely have a huge impact on quantum computing, because now you could do a lot of things, potentially do a lot of things in quantum computing at much higher temperatures with much larger superconducting gaps, meaning stability and so on. So there's a lot of applications of superconductors with higher temperatures. Most of the ones that we've discovered so far that have, not room temperature, but they just are somewhat higher temperatures, like the ones based on copper oxide materials, are not useful for most quantum computing applications because of the details of the superconductivity. They are what are called D-wave superconductors, which are great for superconductivity, but actually are not great for quantum computing, because the D-wave superconductors have something that are called, superconducting nodes in the gap, and they have a lot of excitations around those nodes that are not that bad for superconductivity, but would be extremely bad for quantum computing. So superconductivity is, showing superconductivity is necessary, but not sufficient. There's a bunch of other things that you also need in order to be able to use it for quantum computing devices.
Understandably, and interesting to see how this progresses. What about a few final thoughts in terms of what are you looking forward to in quantum computing and your team's research?
I'd say, like I said, we hit that first milestone. We're making qubits out of this material right now, and so for us, this is an exciting time. Making qubits out of topological phases, characterizing them, building on top of them, changing designs and materials and so on for better performance. So it's an exciting time of seeing topological qubits come to life. More generally, for the field, I think that it's an exciting time that there's been these multi-qubit systems, things like 50 to 100 qubits of these various other types of qubits, and maybe even beyond. And that's when you can do really interesting error correction and realize, what's called a logical qubit or error-corrected qubit. That's a big, scientific and technological milestone for the entire industry and field. And, there's lots of glimmers of that happening across various technologies. So I think that's extremely exciting. So those are kind of the the big things I'd say, which is like, us making a new kind of qubit, and then the industry in general realizing logical qubits.
Yeah, sounds really exciting, and all the best with that.
Thanks.
Who would you like to know more about you or your team's work?
Two groups, so it's a good question. So I think there are within the scientific community, there are many people who, they're busy with their own work. They don't necessarily follow closely what's happening in these fields, but are actually would understand and appreciate it, and enjoy it. So I think that sort of within the scientific community, it would be good for us to communicate to a little, we're communicating to the experts right now, the people who are very deep experts, but to a little bit of a broader community so that they can, maybe even contribute to or figure out how to use or engage with us in some way. There's the wider general public, for whom I think quantum computing is extremely mysterious. And there's a lot of, honestly, there is a fair amount of hype out there, right? Some of that hype is well-intentioned to generate excitement and interest. Some of it maybe not totally well-intentioned, or maybe is a little misguided. I think it's important to engage with the broader public so that they understand what it is that we're doing. That it's not going to solve every problem, but it could solve some very important problems, that the scale we need is very large. It's millions of qubits, thousands of logical qubits, and we're not there yet. We're at 50 physical, we're at 0 logical qubits to the digit, maybe 1 soon. So, to get to thousands of logical qubits, it's still a journey with a bunch of breakthroughs needed along the way. And then, so that's a much wider audience, sort of scientifically curious audience, which I think is probably like the audience of your podcast, right? So I hope that this conversation contributes in a little way to that, positively. And the last thing is, young aspiring scientists who are looking for exciting things to do. I hope we can help inspire them, and that, if they learn something about what we're doing, those might be the people who make the breakthroughs we need.
I sure hope they do. Lastly, a question that I've started asking all of the interviewees, because we do focus on scientists and people working on very groundbreaking tech and science. So do you think that humankind has the ingenuity to solve some of our biggest environmental and scientific challenges?
I think so. I do think so. I think, we have demonstrated over, decades and centuries, the fact that we really can understand very deeply what's happening in the world around us, and that we can use that understanding to build new technologies. And so I do think we have that capability. It's not a given that we'll do it, because we also do engage in a lot of self-destructive behaviors, and don't always appreciate problems as they're coming down the pike. And historically, societies and civilizations have collapsed many times, and so we shouldn't take for granted that we will. I think climate change is potentially, an existential crisis for humanity, and it's not a guarantee that it is, of course, because it is hard to, as Yogi Berra said, it's hard to make predictions, especially about the future. But there is a chance that this is an existential crisis. We are capable of solving problems like this, but we don't always get our act together. So while I'm hopeful, I'm not naive about it.
That's a good closing comment, and let's be hopeful and have a majority of people working on the things that definitely can help humankind overcome some of the biggest challenges we have. Thanks so much, Chetan, for this discussion. I've really enjoyed it. All the best with you and your team's work. You're working on solving some really important problems, so all the best with that, and hope to hear more about your work in the future.
Thank you. Appreciate it.
That brings us to the end of this really interesting episode featuring Chetan Nayak, one of the brilliant minds behind the ongoing quantum revolution. I hope you found this conversation as enlightening and thought-provoking as I did. A big thanks to Chetan and Microsoft for the interview, and of course, thanks to all of you for tuning in. Remember, the quantum revolution is just beginning, and who knows what exciting developments lie ahead. Until next time, stay curious, stay inspired, and keep exploring the limitless possibilities of the quantum world and science in general. This is Joel signing off from Future Here. See you in the next episode. Bye.
Future Here.